Too much. So this is Balch Creek, and this is one of only two perennial streams that flows in all of Forest Park. The other one is Saltzman Creek, which is north of here about 2 miles. So the creek we were at the other day, coming out of Markham Gulch, is not a perennial stream, so it'll dry up in the summertime throughout most of its course, and we'll only have water if we have a storm during summer, which are of course pretty rare around here. On the other hand, this one, as we talked about in class, is fed by base flow. So it has enough of a base flow component that it maintains water throughout the course of the year. So this is a perennial stream rather than an intermittent stream like the other. Depending on what it looks like when you guys get here, as it is right now, there's a pretty high suspended sediment load that's being transported because of the recent rains, and clearly you can see how muddy it is. And so, you know, if you see the stream is highly muddy, that means there's a lot of capacity in this discharge currently, so there's a lot of material that's being transported. But it's not high enough to transport the bed load that we see out in the center of the stream, so that's only at really high flows do you get stuff that's moving quite like that. Just like every other stream, however, in Forest Park, this one doesn't get to go all the way to the river, so this is where it goes into a pipe, and then it's piped from here all the way out to the Columbia River underneath the industrial area up here in northwest Portland. So where we're going to go from here, we're just going to wander just a little bit, and we're going to see some nice examples of mass wasting, and we're going to do a little bit of geomorphology by our feet and by our ears, thinking about stream processes.
Cool.
So this is an excellent example of mass wasting. So when you guys are getting ready for your mass wasting project, which is coming up here essentially this week and next week, again, you're looking for examples of creep or flows or slides or falls. And what we have here is, again, an excellent example of mass wasting. And if you can kind of see, there's sort of a fan-shaped deposit here in front of us. And then there's kind of a little bit of a depression above us. So the source region was almost to the top of the hill and probably caused by heavy rainfalls. And then that material moved down and then deposited itself as a fan, and you can see how it juts out a little bit into the stream. So again, when mass wasting happens, it creates a little bit of a buttress, and then we've actually come back in and put some large rocks here to sort of help stabilize this landslide. Mm-hmm. Otherwise, the stream itself would erode the landslide, and then it would just happen again. Which is totally common in areas that are steep like this, you know, this kind of high energy environment. So in this case, this would be most likely a slide. So it probably started off as one coherent mass, and the reason that I call it a slide rather than a flow, and if you recall, a flow is where there's tumbling material that's moving, and the reason is that there's a whole bunch of trees and some vegetation that look like they might have even, you know, made it through the slide. But nevertheless, we have some new tree growth here. So these are all alders. These are trees that come in as sort of early successional type species after there's been some kind of a mass wasting event, as we see right here. Indication that this is a mass wasting event as opposed to, say, a flood event is there's an area over there where you can kind of see the sediment, and it's a real mixed bag. There's some large particles and small particles that are all mixed together, and the particles are very angular. If this were an alluvial deposit, like a floodplain, then we would expect to see the big particles at the bottom and the small stuff at the top, and they would also be much more rounded from the abrasion factors in stream flow.
Great.
So obviously we've been having a bit of weather lately, some pretty good storms, some pretty snow loading and ice storms, and so there's a tree here that has come over in these storms, and you can see the entire root ball mass. So this is a wind throw event. It sometimes can be by ice loading, but in this case it's probably saturated soils. We had some pretty good gust of wind, and it just knocked the whole tree over, root ball and all. The reason this is important is that this is one way that a lot of material can get moving down slope, as trees get knocked over and then they drag a lot of this material with them. And again, this process is called root throw. And when we talk about weathering, this is one way that there's sort of a biological weathering that can take place through this process. We'll swing over there. One of our forms of mass wasting, and if you're looking for a project, this is the easiest but most boring one to do, and this process is called creep. So if there's a slope, any kind of slope at all, then material is going to be moving down slope gradually due to gravity. And a lot of that has to do, especially where there's saturated conditions. So when the ground gets saturated, it heaves. So remember, all the pores in the soil get filled with water. There's a heave process. And then when that water evaporates or transpires back out of the slope, the particles can't go back to where they started because that would actually be moving up slope. And I'll have you look at that. There's a great graphic of that in your textbook. So instead they move just a little bit downslope, and that process is kind of a ratchet-like process. It's called soil creep. So it happens most rapidly at the surface and then decreases in terms of its rate at depth. So a tree is rooted pretty deeply, but the whole thing is moving down slope. But trees don't like to point anywhere but up, so the tree continues to adjust itself so that it continues to straighten itself out, and what you end up with is a tree with a knee. So trees have knees, and if the knee is pointing down slope, that's a great indicator that that slope is in creep.
So are there times when the knees point upslope?
If there's a slump, if some trees had lived on that last slide that we looked at, then after the slumping, they would be pointed upslope. They would straighten themselves out, and then they would have a knee that points upslope.
Oh, interesting. Okay.
I can't remember if there are any of those here.
So did the creek come up, or did slide stuff come down?
Oh no, I think it flooded.
Creek. Okay.
And it might be from that coarse woody debris over here.
You think it got dammed right here?
Yeah, totally.
And then...
Oh, okay.
Yeah.
Yeah, because like all the moss was stripped off.
Yeah, the flow was going over the top of these logs.
Yeah. And it seems like debris is probably...
Interesting.
Yeah, that's cool.
But that's older than the storm. Okay, so are we all right?
Yep.
Oh, so we just fun little discovery as we're walking on the trail here. This is again doing geomorphology by your feet. We noticed a whole bunch of alluvium on the path itself. So this had become part of the floodplain during the last storm. And so we walk back a little bit, and what we see is what's called coarse woody debris, which just means big trees. So big trees fall in the stream, and it's actually a really important geomorphic process as well as a biological process. And so one thing it did is you can see there's a lot of racked material on the logs, and so that backed up, created a temporary dam. We can see the effects of that by there's a gravel bar immediately behind the dam.
Oh.
So dams decreased the velocity of the stream. As the velocity decreased, then those particles fell out of suspension. But what's great about that is you can actually see how competent the flood is. It was moving things about the size of a tennis ball. So there was pretty good discharge coming through here at that point in time. But the temporary dam then deflected the water, and it couldn't go that direction because it's a pretty steep slope. So instead it came this direction and flooded out onto the trail and came right out. And of course, once it got on the trail, it lost a lot of velocity, so it dumped a lot of its suspended load, really silts and sands, and then kind of drained back around the dam back into the stream. Some geomorphology by our ears. You'll notice I have to speak a little louder. So the reason for that is that the stream is louder. So you might ask, why is it suddenly louder? Well, clearly that means that the velocity is increased. Also notice that the size of the particles in the stream has gotten a little bigger, meaning that at high flow events there's more energy. So what's happening, and we can figure this out, we can see that it's starting to get a little steeper. So the gradient has changed. If you look around behind you, it's a fairly gentle gradient, and there's some pools with a lot of sediment. But as we get to here, we've lost all of our pools, and we have much larger particle size. So it's just simply a matter of, as it gets steeper in the stream, the water can move faster, and the single most important stream process related to competence, or like the size of a particle that can move, is the stream velocity. And as you increase the velocity, you increase the size of the material that can move. So just by increasing the gradient, we increase velocity, we increase the competence of the stream, and you can actually hear that as the water is churning through these small little cascades here. When you're looking for examples of mass wasting, one thing you want to be looking at is the nature of the sediment. And actually through this whole area here, it's a very confused little bit of sediment. There's clearly a lot of rounded material that looks a lot like what you would find in a stream, and so that's definitely alluvium. This is something that's been transported by a stream, and it's tumbling along as it goes through the stream and getting more and more rounded. But then right next to it is something super angular. And so this would not be a stream process, it would be more rounded. So this is more what we would call colluvium. So this is sediment that is associated with mass wasting. So it's stuff that is falling directly out of the hill slope here, and as it lands, you can see there it lands and then shatters into two pieces, leaving those angular fragments. So if you're trying to distinguish, is it mass wasting or is it just flood related, that roundness versus angular is a really good giveaway about, yes, definitely mass wasting versus floodplain type stuff.
So the round ones here have been transported when the stream was really high and throwing tons of stuff off?
Or it could have been when this was the floodplain, and then the stream is incised since that time. So there's a lot of development in this area, so there's a lot more impervious surface. So the runoff has actually increased, so there's been incision at this point. And you can see, so there's old floodplain material over there, all that rounded material. Again, likely when the floodplain is a little higher elevation than it is today.
Yeah, there's a lot of rounded material in there.
Comes up, so once the stream starts to get a little steeper again, the morphology changes again into what we call a step pool morphology. And we actually saw this in the Markham Gulch, at a much smaller scale, but remember that was a very steep canyon. So we had little pools and then steps and a pool and a step. So this is a larger river system, but again it's getting steeper, so now we have a step pool morphology. So we've got the pool, and then the white water indicates the step, and then another pool and a step, and a pool and a step. And the spacing of the steps is largely a function of the size of the particle in the step. And so if you take that particle size and roughly 2 or 3 times that particle size is about the height, or is about the length of your pool, often in the circumstances. This one's been, the last floods have kind of reorganized things a little bit, so it's going to take a time to kind of work itself out into its regular pattern again. It's no great, just small little slides and flows.
Now is there that thing about the bank full width?
That's on meandering streams.
And the distance, oh okay. So we won't see that in this thing.
It's further up, they have it, So it's where you have the riffle pool. So you get the, where it straightens out, where the thalweg is swinging back and forth. So when it goes into the one swing and you get the cut bank, so that becomes your pool. And then it straightens out into a riffle where it kind of shoals out.
Okay.
And the spacing between those is about 2.5 times the bank full width.
Okay, so it was a flow.
So this is a flow event. Again, it's much more devastating looking than a slide event. It's not nearly as hunky. But also you see it's kind of occurred in what we would call a zero order basin, a little bit of a gully, gulch, arroyo, holler, whatever you want to call them. So there's a lot more water that gets involved and it mixes as it moves, so it has this very chaotic distribution. But we talked about viscosity with volcanism, so we could say the same thing. So the size of this particle is pretty large, so it's a fairly viscous fluid that's able to transport really large particles. But again, very angular looking. Some alluvium mixed in.
Okay.
It's already starting to the road.
So did it go all the way across?
Yeah, so that's the fan right there.
Okay.
The stream, you can see where the stream used to flow if you follow the vegetation.
Oh,
line.
yeah.
Follow that bank right there, and then bring it across there. So now the fan is pushed out.
That would have been interesting to watch happen from a distance.
I'm sure a bunch of it went downstream too. Probably that gravel bar down there.
Nice.
One reason coarse-weighted debris is often important is you can see what it's done is it slows the flow. There's a big gravel accumulation and boulders behind it. What this will do is right now there's a lot of water that's moving down into what's called the hyporheic zone. So this is acting as kind of a large storage area for water. And then come the summertime, when the flows are a lot lower, there's a lot of water that's stored there, and it's actually being charged underneath us into the banks. And then throughout the summer, that water will then seep out underneath this log jam and come up on the other side. And at that point, the stream temperature might be really warm because it's summer, but the groundwater coming in is really cool. So it cools off the stream temperatures. And it's not happening here, but in a lot of places downstream, there'll be another little gravel bar. And it's usually smaller gravel. And then that water comes out of the hyperaric zone through there, and it flushes all the silts out of the stream bed, and it makes the perfect salmon habitat. So all the salmon reds are almost exclusively downstream of coarse woody debris deposits because it makes the perfect habitat for them. So it's nice cool water that comes from the summer, brings in oxygen, dissolved oxygen, and then flushes the silts out so the eggs don't get buried. And so there's kind of this symbiotic relationship between Doug fir falling into streams and then creating salmon habitat.
Interesting.
Very unique to...
Really cool. Yeah.
So there'll be less water upstream of one of these than downstream.
Right now, water's going into the subsurface because it's slowing down and charging down into the gravels, and it's going laterally into the banks. So underneath us, the groundwater table is about 8 feet below us, and it's charging all in that direction. And so when the water level drops back down, that water will come back out of the banks, and it'll be like 50 degrees, so it's like perfect salmon temperature. So the stream can go ahead and heat up, and then it kind of moderates the temperature. Yeah.
Great.
The shitty thing about it was that in the late 1800s, this of course was an impediment to navigation.
Yeah.
So we ripped out dynamite and later backhoes, anything to like get these things out of the way before we realized that they were just critical to salmon.
Yeah.
So when people talk about like habitat alteration affecting salmon populations, that's largely what we're talking about.
Okay.
Interesting.
So now the big restoration effort is to go put them back in.
Knock some trees down.
Yeah, people will cut down trees, they'll helicopter them back up in the headwaters, drop them into the headwaters and try to recreate.
Oh my God.
I know, we're nuts. You know?